Welcome, my name is Terry Soule and this is Programming Chaos, a channel devoted to fun and interesting programming projects to help you develop your programming skills. The project that I'm working on today is an evolutionary artificial life model. So we have creatures that you can see here running around and evolving to adapt to their environment. And this is actually the second part in the project. So for the first project, we developed the map, and then in today's video, I'll be programming the creatures. In order to get started, we need to understand a little bit about how the model works. So here's a close-up of the map. We've got some regions that are land and some regions that are water. We have some creatures running around. There we go. And we have food. And for the model that I'm setting up, we have food that's in the water, think of it as, say, seaweed, and food that's on the land, maybe berries. And then one of the key elements is around each piece of food, you'll see this sort of cloud that's basically scent. And so the way the creatures are going to sense their environment is you can see they have these little sense organs, and that allows them to tell whether there's land or water there so that they can steer to avoid the water or avoid the land, depending on which they want, but also they can use them to sense the smell of food, and so they can turn to go towards or potentially away from food. And so those are sort of the key elements. Food has this radius of scent around it, and the creatures have these sense organs that allow them to sense the food through sort of a smell. And this is not too unreasonable. A lot of insects, for example, can basically taste, which is like smell, with, for example, their legs or their antennae. So they can sort of reach out ahead of them and touch the ground and sense chemicals there, which is a form of smell or taste. So not quite as unreasonable as it seems. And the reason that I'm setting it up this way is it becomes very efficient. When a piece of food is placed, we simply place the scent in the environment, and then as creatures move over those cells, they can sense the food. It's much simpler and much more efficient than, say, doing a whole bunch of ray casts to try and imitate sight, for example. And in the previous video, we set it up to create the environment, to add the food, and to add the scent around the food. So those pieces are already done, and I have the code for that here. And so if we run it, here it generates a random map with some land sort of scattered around some water, and you can see it's adding the food, seaweed in the water, and whatever fruit, berries on the land, and around each particle there's that scent cloud. When we created this, it also has the ability to zoom in, which is going to be very handy, and we can use the arrow keys to move around. And so there you can see some food with the scent cloud around it. Now that we have the map done, and again, here's the video if you don't have it and you want to go back and create the map, now we can start adding the creatures. And I'm going to begin with the sort of boring non-evolutionary creatures, but it's a good place to start. So let's create a new class. And our creatures, to begin with, are going to need a position and a heading. And I'll just set those randomly. And then to get anything at all interesting, we'll need to also be able to display them. There we go, and I'll display them by translating to the correct location, rotating so they're heading in the right direction, and then for now just drawing a little arbitrary ellipse, and they're all going to be red. And eventually the color and maybe the shape will evolve, but for now this just allows us to create our population of creatures and display them. Go, closing bracket there. So now I can come over here and create my population of creatures. And I'm going to begin by defining a minimum population size. So in evolutionary models, it's quite common where the initial random creatures are very maladapted to the environment and they all die out and you have an extinction event, which is not very interesting. And so what I often do, and tends to work well, is to set a minimum population size. And if the population drops below that, you just add some new random creatures. So you maintain a minimum population until the population can evolve to the point where it's well adapted to the environment, and then it presumably will rise above the minimum population and stabilize on its own based on things like how many resources are available. So that's why this isn't the population size, it's that sort of minimum population size. And once we have that, we can actually create the population. So my population is going to be an array list of these creature objects. And the reason it needs to be an array list rather than just an array is because the size of the population will fluctuate over time. And now I can add my initial creatures to the population. So that will add my 100 creatures to the population, and then I want to be able to display them. There we go. So there's our map, and in addition to the food, you can see there's 100 of these little ellipses representing creatures. They don't do anything very interesting yet, they don't even move, but there they are, there's our population. And so now let's at least set it up so that they start moving. So I'll create an update function for that. And I'll begin by giving them a speed. Speed is one of the things we're going to want to evolve. And in fact, we'll get a little more complicated and have a water speed and a land speed, which will be different and evolved. But for now, we'll just put in a speed so we can get started. And then the new position of the creature is just that speed based on the sine and cosine of the heading. So we'll use a little bit of trig to figure out how much it should move in the x direction and the y direction based on its heading. And then finally, we want to make sure they stay on the map. In this case, I'm not going to do a wrapped map. That doesn't work very well because in the long run, we're going to have creatures, hopefully, that evolve to prefer to be on the land or the water. And because our map isn't symmetrical, if they run off one side from the land, they might end up in the water on the other side. So instead, when they get to the edge of the map, I'll have them turn around. There we go. So if they go off the map in either the X or Y direction, they'll turn around. That is, I'll add pi to the heading, and then I'll re-add the position, which basically will cause them to move back to their previous position and back onto the map. And so if we run this, we should now be able to see them moving around, except that I forgot to call the update function. So let's come over here, and before we display the creatures, we'll ask them to update their position. There we go. Now you can see them moving around, and if you watch when they get to the edge of the map, they bounce and basically come back. So we've got our creatures and they're moving around. There's a bunch of things they're not doing. They're not eating food, they're not reproducing, and they're certainly not evolving. So we need to set all of that up. And the way that I'm going to do it is I'm going to give the creatures a genome, which is just a series of values that control things like how they look and how they behave, how they interact with the environment. And so one of the very flexible things about this project is you can add lots and lots of different genes to the genome. I'm going to try and keep it fairly limited so that we have a reasonable project to do in a short amount of time. So the idea here is I'm going to add to the creature, as I said, a genome. And that genome is just going to be an array of values for things like how far ahead does the creature look? That is, how far away are its sensory organs, and what is the angle for them? And if it senses water or land, does it turn towards or away from it? If it smells different kinds of food, does it turn towards or away from it? And so in a sense, what we have to decide in advance is what genes do we want to include in the genome. And I'm going to do that using a map function in the main code. So I'm going to create a hash map, which maps particular genes to the integer value that we then look up in the array. And this will make a little more sense once I put in the code. There we go. So what a hash map is a listing of values that are mapped together. You also see a similar structure called a dictionary. And in this case, I want to map particular strings, the names of the genes, to the integer values, which is where we'll look them up in the genome. And so to do that, I need to add a bunch of values to the hash map. So I'm going to put, to begin with, in the hash map of genes, angle, which will be mapped to 0. And in this case, angle is the angle of those two sensing organs. So are they straight ahead or are they off at some angle? And that's going to be allowed to evolve. And that will be gene number 0 is the angle gene. And now I'm going to put in a bunch of other genes that I've sort of decided upon in advance, and then I'll talk about what each one of them does. There we go, and I see I misnumbered these, so I missed number 2, so let's go back and fix all of this. This list of genes came from quite a bit of pre-planning, which I'm not including in the video, but you can sort of imagine. As I said, angle is the angle of the sensors. Distance is the distance out that the creature sends. So that has to do with where those two sensing organs go. Appendage is going to be, in a sense, whether they've evolved a flipper type tail, which is going to be good for swimming more effectively in water, or legs, which are going to make them move more efficiently on land. So I'm trying to get creatures that evolve to either be sort of well suited to the water or well suited to land. The turn speeds are if they sense, that is, they smell fruit, do they turn towards it or away from it? And similarly for turning towards or away from land. And what will end up happening is if they sense land with both, then in a sense there are two turns, to the left and to the right, and they cancel out and the creatures keep going straight. Shape is just the shape of the ellipse so that they can be longer and thinner or wider. Then I'm putting in how much energy they get from fruit or seaweed. And I'm going to put in a normalization factor, and we'll see that in the code a little later. But the idea is if they get a lot of energy from fruit, they don't get as much from seaweed, and vice versa. And then finally, speed is sort of the base speed of how fast they move, which is adjusted by whether they have a tail or legs. And a lot of what I'm going for here is what's known as epistasis. Epistasis means that the value of a trait or of a gene depends on the value of other traits. So a sort of silly question, but I'll ask it, how valuable are lungs? Well, if you have legs to walk around on land, then lungs are great. On the other hand, if you have flippers for swimming in the water, lungs are maybe not so useful. And so that's the idea behind epistasis, that a particular trait or a particular gene value can't be measured by itself. Its evolutionary value depends on a whole bunch of other values. And to get interesting evolutionary outcomes, you typically need a fairly high level of epistasis, which is what I'm going for here. So turning, for example, towards fruit is generally a good idea, but it's much more important if you get a lot of energy from fruit. And whether or not turning towards land is a good idea depends on whether you get more energy from fruit or from seaweed, and also what your appendages are. So if you've evolved a tail to swim efficiently, but you keep turning towards the land, that's maladaptive because those don't align. So I'm trying to include traits that have to line up so that we can get more interesting evolutionary outcomes. This defines all of our genes, and I'm sure that in looking at the model, you already have ideas for lots of other ones, easy enough to add. So there's all of our genes, and again, an easy list to add to once you see how all of the code works. And now the last thing I want to do, now that I have the genes put in, is to have the number of genes, which we'll use in other places in the code, which is based on the size of that hash map. So if we add more genes, the total number of genes automatically changes. And now we can go into the creature code and as part of the constructor, set all of those values, and I'll just set them randomly for now. So there's the array. And we set all of the gene values in the genome to a random number, and I'm doing it from -5 to 5. And this is where things get a little more interesting. So these are the gene values, and over time they're going to be allowed to mutate, and they're going to be allowed to basically take on any value potentially from -infinity to infinity, although I certainly don't expect them to change by that much. But those are not necessarily good values for things like the speed. I don't necessarily want creatures that could go infinitely fast. And similarly, I don't necessarily want creatures that can get an infinite amount of energy from eating a single piece of food, even though I would like them to be able to adjust that. Basically, sort of, is their metabolism well adapted for eating seaweed or fruit? So we need some way to allow the gene values to vary through mutation sort of as widely as we want, but we would like the trait values, so the trait is what we observe, to be more limited. And a really good way to do that is to use what's known as a sigmoid function. So you might be familiar with these. They also come up in neural networks quite a bit, and let me show you one. So this is a sigmoid function. Sigmoid is basically an S-shaped curve, and the idea is we have the gene values along the x-axis, and they can really go from -infinity to +infinity, so we can go as far as we want in either direction, but then they're mapped to a trait value. And you can see near 0, we get fairly rapid changes. So a small change in the gene value creates a large change in the trait value. But as we get to more extreme values, you get smaller and smaller changes. So if a creature is already well adapted to eating fruit, for example, its metabolism, if you will, handles fruit well, increasing that gene value will create a small improvement, but not a very big improvement. And we can change the slope of that curve. So here I've got sort of a very steep sigmoid in blue and a slightly less steep sigmoid in orange. The formula for the sigmoid is this. It's the gene value G is here, and the actual formula is 2 divided by 1 plus e to the -r times that gene value -1. And the 2 and the -1 are actually rescaling factors. So if you leave those out, you get a sigmoid that just goes from 0 to 1, which is not what I want. I want one to go from -1 to 1. So I multiply it by 2 and subtract 1. The R value defines what this slope is, and I'll very arbitrarily use 0.5 for my R value. And then again, G is the number for the gene, and T is the actual trait value. This way we know that our numbers are always between -1 and 1, and then we can scale them further if we need to. So for example, if we're picking the color, I would take this and rescale it from, say, 0 to 255. If I was dealing with the speed of the creatures, I might say I actually want the maximum speed to be 5, so I'll take the trait value and multiply it again by 5. But this way I always know that the value I get back from the gene is from -1 to 1. So I'm going to create a sigmoid function to calculate that for us. And I'm going to put the sigmoid function as part of sort of my main code. It's just a helper function. So there's the R value. I said I'd be using 0.5. And there's the rest of my sigmoid function. There's no rule that says you have to use this. I just find that it makes it much easier to think about the scales of traits to get a well-balanced evolutionary system. So now that we have the sigmoid, we can go in and start calculating the actual trait values for the creatures. So I'm going to do two things. I'm going to add some trait values that we'll use a lot, and then I'll add a function to calculate those for us. So there's a few of the traits that we want. How fast is the base speed of the creature, and then how fast is it adjusted for being on land or water? How much energy does it get from eating fruit? How much energy does it get from eating seaweed? We might also want to add, for example, a color. What color is the creature? And although it's not one of the traits, I'm going to add it here before I forget. How much energy does the creature currently have? So they lose energy as they move around, and they gain energy by eating food. And the way I'm going to set this up is if they get enough energy, then they get to reproduce. Those are sort of the traits that we need, and now we need to calculate them. And I'm going to calculate those values as part of the constructor. So every time we construct a new creature, we calculate these values. So this is a good place to start. I want to know what is the base speed for a given creature. And I'm going to say the base speed is 0.5, so they tend to move ahead, plus a value that depends on their genome. And so you'll see this construction a lot. I'm going to the genes, that is my map of genes to values, and I'm saying, well, get the integer that corresponds to speed, and use that to get the right value out of the array. So I don't have to remember this, thankfully, but if I were to go back to my main code and scroll back up to my map of genes, speed was gene number 10. And so what's happening in the code here is genes.getSpeed gives me the value 10. And so I'm effectively looking in the genome for the 10th gene. And then I'm running it through the sigmoid, so I get a value from -1 to 1, and I'm adding that to 0.5. And if you think about it, what this means is the maximum possible speed is 1.5, and the minimum possible speed is actually -0.5, which means they're moving backwards. And if those are too slow for the map that you have, you could add a scaling factor in front here and say, well, I want to double all of the speeds, for example. But this is a good place to start. So that's the base speed, and then I'm going to calculate from that what should be the speed in the water or on land. So there's the water speed. It's the base speed multiplied by 1 minus the sigmoid again of the gene value for appendage. So the way I'm thinking about this is if appendage is negative, that means they have a tail, and that makes them faster in water. So I get the gene value, so that's from the genome. If that's negative, I'm going to run it through the sigmoid and actually get a negative number between 0 and -1, and I'm going to subtract that, so this will become larger. Say it's negative 0.5, this becomes 1.5 because I'm subtracting a negative number, and so the speed in water goes up by 50%. And again, this is where the sigmoid is handy because I know that it limits me from -1 to 1. And so that becomes a little clearer maybe if I add the land speed. And here the difference is I'm using a plus sign, so I'm adding it. So if we have a positive value, a positive gene value for the appendage, it's going to increase the land speed but decrease the water speed, and vice versa. Okay, so that gives us our land and water speed. And the other things that I wanted to calculate was how much energy you get from eating different kinds of food. And again, I want that to be evolved, sort of different forms of metabolism. And I'm going to do that by normalizing the value. So I'm going to take what is the gene for, say, eating fruit, and divide it by the sum of the fruit and the seaweed gene. So if both of those genes are equal, say their value happens to both be 3, then I end up with the fruit value 3 divided by the sum, which is 6, and it only gets half as much energy from fruit as it might otherwise. But because they're both 3, the same thing is true for seaweed. It's 3 over the sum, which is 6. So you can evolve, in a sense, a balanced gene. I get equal amounts of energy from fruit and seaweed, and sort of a generalist. Or they can evolve to say, well, I want a very high value for fruit, maybe 10, and a very low value for seaweed near 0. And then what I end up with is 10 divided by 10 plus 0, which is to say 10 over 10, and you get 100% of the energy from fruit. But for seaweed, you put the 0 in the numerator and you get 0 over 10 and you get 0 energy from seaweed. So a little complicated sounding. Maybe the code will make it clearer, but it's basically take the amount of energy or the gene value for fruit and divide it by the sum, which has the effect of normalizing them. And so the first thing I'm going to do is calculate that sum, which is the denominator. There we go. As I said, I take the fruit energy value and the seaweed energy value and add them together. In this case, I don't want to worry about pluses or minuses, so I'm just going to take the absolute value of both. And so that means a very high positive value for fruit energy or a very low negative value for fruit energy. Both means the same thing, a metabolism that's well adapted to fruit. And then the one other thing I'm doing is I'm adding in a +1 because this sum is going to be my denominator, and there's always the off chance that both of these genome values are 0, and I'd get a divide by 0 error if I didn't add in some factor. So it's actually going to be over 1. And so now that I have that denominator, I can calculate the actual energy that they get from fruit or from seaweed, and that's going to be my trait value. So energy fruit or energy seaweed. There we go. So once again, I get the gene value and run it through the sigmoid and take the absolute value because I always want to get a positive amount of energy. You could actually remove the absolute value and then in some cases they would lose energy. That particular food source would effectively be toxic, if you will, to the creature. I don't want to mess with that. I divide it by the sum to sort of normalize it, and then just because of the way I'm scaling energy, I'm going to multiply that all by 200. So when they eat a piece of fruit, they get quite a bit of energy. It would simplify the code quite a bit to remove this genes.get and just replace it with a number, 4. Gene number 4 is how much energy I get from fruit. The problem with that is then you always have to remember those numbers. Was it 4? Was it 5? And if you put in the wrong number, the code will still run fine, just the evolution will get completely thrown off because you'll be using the wrong gene for the wrong trait. So it's worth using map to make sure that you get these correct. And now I'm going to do the same thing for seaweed. There we go. And I'm also going to put in color here, so the color of the creatures. And there isn't a trait value for that. You could put one in, so we could go back and add to our genes a color, and then color would evolve independently of anything else. But it's often nice to tie traits that are in some sense invisible to traits that you can see. So there's no way to see how much energy a creature is getting from fruit or from seaweed other than printing some numbers as the program goes, which I don't want to do. So instead I'm going to tie the color to the fruit energy and the seaweed energy values. And I'll set it up in a very simplistic way. If the amount of energy they get from fruit is higher, they're going to be red. And the more energy they get, the higher that gene value, the redder they are. And vice versa, if they get more energy from seaweed, they're going to be green. And so it'll be very easy, or at least easier, to look at a creature and say, oh, that's a red creature. It gets a lot of energy from fruit. So there's my condition. If the fruit energy genome, the absolute value, because that's all I'm interested in here, is larger, so the absolute value of that gene is larger, that means they get more energy from fruit, and I want them to be a reddish color. So there we go. Because the fruit energy gene is higher, that means they get more energy from fruit. So I'm going to use that gene, run it through the sigmoid again to get a value from -1 to 1. Take the absolute value, so I actually get a value from 0 to 1, and then I'll multiply it by 255. That'll be the amount of red, and I don't have any blue or green in this case. So a lot of red means I'll they get a lot of energy from fruit. And otherwise, I will do the same sort of thing, except that I'm going to use green and the amount of energy they get from seaweed. And I realized I wanted that to be green, not red. So the amount of red is 0. This is the amount of green. And then the amount of blue is 0. So there, that will set the color, again, based on how much energy they get from each. And these are all values that are calculated once when a creature is created. And now I can go in and modify my code to take advantage of those values. The first thing I want to do is in the update function, change the speed based on whether the creature is on land or water. And where this gets interesting, the creature is in an absolute XY position, but the land and the water are in these grid cells. So the map itself is sort of on a coarser grid scale. And so I need to translate my XY position into the map coordinates. That makes this code maybe a little more complicated than you might expect. So I'm doing an if, I'm taking the y value, dividing it by the scale of the cells. So if my cells are 3 by 3, I take the y value divided by 3 to figure out which cell I'm in terms of the map, and then use the int to make that an int value. And as always, because I'm converting from an XY position to a row column in a two-dimensional array, the y goes first and the x goes second, which is a little odd. But this tells me which cell in the map the creature is in, and then I get the altitude, and if it's less than if it's less than 0, that means I'm in water. And so the speed I want to use in that case is the water speed. And so now I'm updating the speed based on the terrain that the creature is in. And then we can also make some changes to the display function. So for one thing, I can fill with my color. The other thing I might want to do is adjust it so that we can see that tail or see the legs, because that's not part of the model yet. So the first thing I want to do is get a value for what that appendage gene is. So there we go. I'm just, as always, getting the gene value from the genome and then running it through a sigmoid. And again, if it's negative, that means that I want a tail to represent creatures that are fast in water. If it's positive, I'll put in some not very good legs to represent a creature that's fast on land. So one of the things I'm going to do here is a separate little bit of scaling just for the appendages. So I'm going to do another push matrix. And I'm going to scale based on the value of the appendage. So if it's near 0, I'm going to end up with a very small tail or legs. If it is evolved to be near 1 or -1, because I'm going through the sigmoid, then I'll get a bigger tail or legs. If append is less than 0, then I want to put in a tail. And I want the tail to be at the back of the creature, so I'm going to translate to the back of the creature, which is based on the size of the cells. So I'm going to change my ellipse here in a minute to be based on the size of a cell, and then I can put the tail at the back. And I think I'm going to make my tail wave back and forth just to make things a little more interesting. So there's a little bit of rotation when I put the tail in based on the frame count, and it's the sine of the frame count. So I'll rotate back and forth as the frame count increases. Adds a little bit of flavor. I have a previous video on creating swarms of sort of simple bugs, and that includes some of these same ideas. So if you want to make your creatures look more complicated, that's not a bad video to go back and check out. And now to keep things simple, I'm just going to make my tail a triangle. So I've translated to the right location, so that means I can start at 0, 0. There we go. So there's my triangle, and the true size of that triangle is defined by this scale up front. So depending on how strong the appendage gene is, we'll get a bigger or a smaller tail. And that's if the value is less than 0. Else I'll just put in a couple of legs. And so there we go. That's just going to put a line basically through the middle of the creature, the width of 2 cells. But again, because of this scaling factor, it may be shorter than that if the gene value is fairly low. So higher gene values will see either longer legs or a bigger tail, which will also reflect faster movement either on water or on land. Okay, and we could add additional lines to have more legs, and we could put in a rotate to make the legs move. I'm not going to mess with any of that for now. And I want to pop this matrix, which is just removing the scaling function. So the scaling function only applies to the appendages. I'm going to remove my stroke. And so I should make sure up here to put in a stroke. And I'll just make it the same as the fill color for now. And then, like I said, with the ellipse, I want to adjust it. Instead of just being this arbitrary 10 and 5, I'm going to adjust it to the scale of my cells. So the first value is going to be the size of a cell. That's sort of the length. And then the width is going to be based on the shape. And when I say shape, I mean that shape gene that we created. There we go. So they'll be wider or narrower depending on the value of this gene, which again, I'm running through a sigmoid, so I know that it varies between -1 and 1, and then I can add it to 1. So hopefully, if this is all set up correctly, and there's a lot of code, so a good chance that there's some typos to fix, but if not, we'll now get creatures that have sort of a tail, sort of legs, and behave differently in terms of their movement speed on land and on water. So let's go in and see. We probably need to fix a little bit of code. So an incomplete statement, this is pretty typical. Make my window a bit bigger so we can see. Okay, so first problem, genome is my array, so I don't need those parentheses. I just need to get the value out of the array. Second issue down here, I misspelled altitude. There we go. And then the third issue is misspelled seaweed energy there. So I can correct that. Let's see if that will run now. So there we go. We have creatures moving around. You can see they tend to be different colors. So some are green, which implies that if they could eat food, we don't have that in yet actually, they would get a lot more energy from eating it. And this creature, you'll notice, for example, is moving very slow in the water because it has a pair of legs. So all of these leg creatures are moving fairly slowly, but oh, just missed it. There was a creature that was moving very fast in the water, but slowed down as soon as it hit the land. So if we watch it, once it hits the water, because it has a tail, it's going to speed up nicely. And so you can see the creatures, they're not adapting, they're not evolving yet at all, but we can see if they have tails, they're very slow on land, but fast in the water. In some cases, they can go backwards because the base speed can be negative. So we have the variation that we need, and the variation is tied to the environment. What we're missing is the ability to do things like eat food, to turn towards or away from food, to turn towards or away from water, to reproduce. If you get enough energy, we'd like our creatures to be able to reproduce. So there's a whole bunch of things missing still from our evolutionary model, but this is probably a good place to end this video before it goes on too long, because now we have the creatures with the variation built in. And then in the next video, we'll add the ability to eat food and to evolve over time. And the big things we need for evolution is eating food, starving to death if you don't get enough food, reproducing if you eat lots of food, and then things like mutation. So if you reproduce, we'll have an individual that splits off an offspring and will mutate that offspring. Okay, so I will wrap things up there. Thank you very much.